Hi all, welcome to the next lecture on quantum mechanics. So in the previous few lectures, we have got the background, the knowledge required to define Hilbert space. Now it is a time to define what is meant by Hilbert space. So Hilbert space is again a linear vector space which has to satisfy certain conditions. So the first thing we can write is it is a linear vector space. And the second thing is we have to define the inner product between the vectors in that the linear vector space. The inner product is defined. What's in the inner product? So inner product phi comma g, or better we can write f comma g would be equal to g comma f compress conjugate, and f comma g plus h must be equal to f comma g plus f comma h, and so that's called the distributive property, and f comma c into g is simply c times f comma g, and inner product with itself will be always a positive quantity. And we define the norm with the inner product. The norm of a vector is the inner product with itself, always 1/2. So if these two conditions are satisfied, then that vector space is called unitary space. Okay, linear vector space with inner product defined. Okay, so these are the two conditions, and the third condition, that vector space must be separable. And what is by separability condition we have discussed in the last class, and the last condition is completeness. So if an vector space or linear vector space satisfies all these conditions, then we can call that vector space as Hilbert space. Okay, so it's very simple, and if you remember this definition, that is enough for us. Okay, so what is the importance of the Hilbert space? It is the linear vector space with inner product defined and a separable and completeness property. Okay, so I think we should give some time to discuss what is by completeness in detail. Okay, so in order to discuss that, we have to go for what is meant by the basis and dimension of vector space. Okay, so basis vector is just a set of linearly independent vectors. A set of linearly independent vectors are called the basis vectors. So we can start with very simple example. So consider Euclidean three-dimensional vector space. So we are living in Euclidean three-dimensional vector space. Our physical space is a three-dimensional vector space. So there we need three vectors I, j, k. So these I, j, k can be taken as basis vectors. Now remember, this is not the only choice available. This is only one choice. The other choice can be r theta phi is another choice. Is also basis vector. Okay, and this basis vector, the basis vector that I have written here as a special condition, that these vectors are orthogonal and its length is unity. So therefore, these basis vectors are the examples for orthonormal basis vectors. Now, again, this condition, this orthonormality is not a required condition for basis vectors. Okay, the basis vector need not be orthogonal. It need not be normalized. Only thing is it must be linearly independent. Okay, so this is the basic definition. This is a basic definition for the linear vector, the basis vectors. So it must be just set of linearly independent vectors. Okay. Now again, you must have confusion. What is meant by linear independency? Okay, so this ijk is called linearly independent. Okay, so the condition for linearly independent we can write first. What is meant by linearly independent? Okay, so consider some C1i plus C2j plus C3k. Now this becomes 0 only if C1 equal to C2 equal to C3 equal to 0. So the sum of three vectors ijk would be 0 only if their corresponding coefficient is 0. If that is the case, then the vectors ijk is called linearly independent. That means it is not possible to write I in terms of j and k. Okay, so I is independent with j, I is independent with k. So how can you extend this definition? So consider a linear vector space with vectors phi1, phi2, phi3, etc. up to phi n. Now these vectors can be linearly independent if a1 phi1, or okay, better we can write c1 phi1 plus c2 phi2, etc. up to cn phi n equal to 0 only if c1 equal to c2 equal to up to cn equal to 0. If this is the case, if this sum is 0 only if their coefficient is 0, then we can say that phi1, phi2, phi3, phi etc. up to phi n are linearly independent. Okay, so if suppose this becomes 0 if any one of it does non-zero. Okay, let us suppose c1 and c2 are non-zero, then we can write phi1 in terms of phi2, isn't it? That is, if c1 phi1 plus c2 phi2 equal to 0, with c1 not equal to 0, c2 not equal to 0, then I can write phi1 as minus c2 by psi1 times phi2. I can express phi1 in terms of phi2 if it is if their coefficient is non-zero. Okay, so if any two vector is called linearly independent if its linear combination is 0 only if their coefficient is okay. So that is a condition for linearly independent. So if phi1, phi2, phi3, etc. up to phi n are the maximum number of linearly independent vectors in a vector space, then we can treat this as a basis. Okay, so it is just collection of just linearly independent vectors. It need not be orthogonal. It need not be normalized. So, but if it is orthogonal and normalized, then we can call it the orthonormal basis, like in this example. So here it is an orthonormal basis. Why it is orthonormal basis? Because the dot product between the scalar product between any of two basis vector is 0, and the length of each of this basis vector is 1. It is normalized, okay, unit norm, and they are orthogonal. So that is why it is called orthonormal basis. Okay, so what is a basis? Basis is a set of maximum number of okay, suppose if it's 5, 1, 5, 2, etc. up to 5n is a maximum number of linear independent vectors, then this we can treat as a basis. Okay, then if you take the linear superposition of 5, 1, 5, 2, etc. up to 5n, this becomes 0 only if C1 equal to C2 equal to C3 equal to etc. up to Cn equal to 0. Now here if you add any other vector, okay, maybe psi, then that superposition can be 0, C2 phi 2 plus C3 phi 3 etc. up to Cn phi n plus psi. It can be 0 even if C1 not equal to C2 not equal to etc. Cn not equal to 0. That is possible. Okay, that is, so that means the psi can be written as minus C1 phi 1 minus C2 phi 2 etc. up to minus Cn phi n. Or psi we can write as sum over I equal to 1 to n Ci phi I. So what I am going to say is, if you have, okay, but it's plus Ci or minus Ci, that doesn't matter. We can include that here itself. Okay. So what the point that I am going to make is, if you have a basis vector, the set phi I, then any other vector in that space can be expanded in terms of basis vector. Okay. So if you have a basis vector phi I, then okay, what we can do is better we can write minus psi equal to 0. Then C is plus phi 1 plus phi n. Better we can write it is Ci. Okay, so the any vector in the vector space can be expanded in terms of its basis. This is what I am going to mention here. So any vector in general can be expanded in terms of basis vectors. Okay, now if phi I phi j equal to 0, if I not equal to j, if I equal to j, then it must be non-zero. That is that we know, because that is the norm of vector with itself. It should be positive. It cannot be 0. So if phi I phi j equal to 0 and I not equal to j, then we can call that basis is orthogonal. So this is what is called orthogonality condition. Okay, so if the inner product between or scalar product between any two bases is 0, then we can call that basis is orthogonal. And if phi I equal to 1, that means the norm of phi I equal to 1. So that means it is a normalized vector. Normalized. So the basis is normalized. So how can we combiningly write this? That is the combiningly that both the orthogonality and normalization condition we can write the scalar product phi I phi j equal to delta ij, where delta ij is canonical delta. The delta ij equal to 0 when I not equal to j and equal to 1 when I equal to j. So this is called the orthonormality condition. So if basis satisfies this condition phi ij equal to delta ij, then we can call that basis is orthonormal basis. Okay. Now, at last, we have to define what is meant by dimension. So dimension is just the number of basis vectors. That's it. Dimension is simply the number of basis vectors. For example, in case of three-dimensional vector space, we have only three basis vectors, I, j, k, or r, theta, phi. So this is a case of three dimension. And if you have phi 1, phi 2, etc., phi n, if you have n basis vectors, that means it is n-dimensional vector space. So the dimension of vector space, depending upon the maximum number of linearly independent vectors in it, or it is a number of basis vectors. So it is nothing but the maximum number of linearly independent vectors in vector space. Okay, so that's enough for the time being. So we have started with the definition of the Hilbert space. The Hilbert space is a unitary space which is separable and complete. And after that, we have defined what is a basis. A basis is just set of the linearly independent vectors or maximum number of linearly independent vectors in a vector space. And once you know the basis vectors, we can define or we can express any vector within that vector space as the superposition of the basis vectors. So that is the main idea. And a vector space is called or a basis is called orthonormal if it satisfies this particular condition, the orthogonality and the normalization condition. Then it is called the orthonormal basis. And finally, the dimension means the maximum number of linearly independent vectors or the number of basis vectors in a vector space. Okay, so with this, we can stop our discussion now. We'll see with the new topic in the next class.